Time of year to revisit our old friend, the ozone hole, in the southern hemisphere springtime, which is our fall. Sometimes there's interesting ozone holes in the northern hemisphere, but this is about the southern hemisphere. All right, if you go to a typical website and, oh wait, if you Google Weather Watch, do you know what you get? Just, you get watches with weather things. Sorry. But if you Google, ozone hole, then you'll get to a website that shows this. It's a NOAA representation of the way they do it. They show the ozone hole area and the ozone hole minimum value, and it's averaged from September 7th through 13 October for each of these years. So what we can see is that this year and last year are in the top 20% of the size of the ozone hole and also the minimum value, which these are around 100. This is 100. So as you know, it started to decline in the 70s and 80s, and then it's been roughly steady. We're hoping that it'll recover and return, but if you think about, I think the loading in the stratosphere is still 2.5, 3 parts per billion, so for chlorine. It just takes a long time. So if you think about a particle of air arriving over the South Pole, it probably went through by way of the mesosphere, which takes 10 years to get there if you heat it 1 K per day to get to 5,000 Kelvin. And so the arrival time, the age of air crossing into the stratosphere and then descending in the polar vortex, really long tail. So that's one way to say it's going to take a while to cleanse out the CFCs.
I thought the original estimate was 30 years.
Well, yeah, hopefully, yes. The time that's often tossed around is by the year 2060, but after a while it'll be 2070, will be exactly normal. I don't know, there's still chlorofluorocarbons.
I guess 30 years is like a knee folding line or something like that.
Yeah, pretty long tail for that. It takes a while for it to get up there, into the stratosphere, and then into the mesosphere, and then finally catalytically broken down and combined with other products and back into the troposphere. Okay, so what I thought was, I kind of want to make a comparison for myself of 2 different ways of expressing this. And so I made this last night. I just downloaded some stuff, some data, and put it into an Excel spreadsheet. So I haven't spruced it up yet, but there's 2 ways that people talk about this. So this is the Southern Hemisphere annual maximum ozone hole area from 79 through 21, so 1 dot per year. The orange curve shows the ozone hole area, and it's in millions of square kilometers, averaged during that period. So you take every day and average all of those days. But the blue is, during that period of time, which daily maximum was the largest? And so it's always a little bigger. 2 interesting years, I guess a third one there, 2019, but most often people talk about 2002 and 1986 as anomalous years. This is because of, well, you know about sudden warmings in the northern hemisphere. They're very rare in the southern hemisphere. This involves a large amplification of planetary waves, and we call it wave driving. Or you could express it in terms of the polar heat flux, B prime, T prime, at 100 hectopascals. That's the upward energy propagation for Rossby waves. In those 2 years, there was a lot more of that, and the vortex slowed down and got warm. So it's anomalous. And the ozone hole did not proceed as long or as extensively as normal. So we'll get into that a little bit and compare heat fluxes in the northern and southern hemisphere briefly. This isn't very long. It's just 10 intro slides that I downloaded, and then 3 movies, very short movies. All right, if you do the same thing for southern hemisphere annual minimum column ozone, then the curves are reversed, where you get to a deeper minimum if you look at the daily deepest one out of that whole time period. Whereas if you average for this period of time, then you don't get quite as deep. And again, less deep ozone hole, not as bad in these 2 years. Also this one. So that's pretty strong evidence that out of this data record, there were about 3 years where there were sudden warmings, or close to it, in the southern hemisphere. This is just a background slide to show the vertical regime. All winter long, you have a lot of ozone making its way forward and downward and sinking and accumulating under pressure, and so you have a high column amount. But the temperature profile is C-shaped in the stratosphere over the South Pole in the winter, and you can see sometimes it gets really cold in this region. There's the temperature scale. less than 192 Kelvin, you'll form nitric acid trihydrate droplets. And that catalyzes the conversion of chlorine reservoir species to Cl2, which then, when the sun comes up, so this is before the ozone hole for that year, and this is afterward, you can see this bite taken out in the layer approximately 14 to 22 kilometers. That's where the PFC clouds live. That's where the chlorine compounds are catalyzed to Cl2. And when the sun comes up, so you need all these things, then finally you get an ozone loss, and it's rapid. That happens in 4 or 5 weeks. Here's the time signature. You can see going towards southern summer, the warming of ozone in the upper stratosphere. And this cold period is pretty deep. It lasts quite a while, but it wanes going into, as the sun's coming up in the southern hemisphere. It's starting to warm. But that region is where you can form nitric acid trihydrate in time and altitude. So this is relevant to the heat fluxes of planetary Rossby waves in the southern hemisphere. E prime, T prime, and K in kelvins times meters per second. You can see that negative values increase this way. A heat flux toward the pole is negative, it's southward. And so a strong one like 2002, I think that's probably 1986 and 2002. You can see that it's a much stronger polar heat flux, and this axis shows that the polar temperatures are warmer. So a range of maybe 25 degrees depending on, from year to year, depending on the amount of wavy disturbance.
And so, if I recall, that polar heat flux is indicative of waves propagating from the troposphere into the stratosphere, correct?
Absolutely. So if you think of the vertical component of the Eliason-Palm flux is B prime T prime bar. That is the vertical component. So if you have a westward tilt and you're releasing available potential energy, that's tantamount to a polar heat flux. You're reducing the center of mass. Another way to think of it is in linear theory, linear wave theory, the group velocity for Rossby waves, GZ, is upward, and it's close. GZ times the wave activity is the upward component of the EP flux. So here's an example from this year. This is 2021, and it's V prime T prime at 100 hectopascals. There's a running 10-day mean, and you can see, well, here's springtime going in, fall going into winter. It slowly picks up, look, maybe 2, -5, maybe some -10 peaks. And then often this happens when the westerly winds in the southern hemisphere, they're so strong because of the rate of driving, and the wave activity is weak enough. There's a regime where the winds just cause the wave energy to refract and go back in the troposphere. It's trapped. There's a turning level associated with strong winds. So usually in the middle of the winter, waves are prohibited from entering the polar vortex in the southern hemisphere, and it gets stronger and colder and stronger and more resilient. But when the sun starts to come up, there develops a regime which is often a dumbbell-shaped propagating pattern of wave number 2 that travels about 25 meters per second, slower than mean wind. So it's a little westward relative to the flow, but it goes around clockwise when you look down. And then getting into the springtime, there's more wave activity that can penetrate into the stratosphere because the winds are weaker. Some years, I suppose this is 2002, you get quite a bit of heat flux. That's not too bad, 40 of these units. We could compare that to the signature in the northern hemisphere. This is from just this past winter, and I was trying to remember, well, kind of a relative lack of wave driving here compared to this green line. So this is coming out of our winter. Typical values, 10, 15, 20. That's a lot bigger than down in this range for the southern hemisphere. So the winter, there's a lot more wave driving. The continentality, the contrast of land sea, the mountain ranges, and the variability just leads to stronger planetary wave activity in the stratosphere. Then they don't get into summer easterlies, so there's a diminution, then they come back up in the fall and winter. But maybe 5 times bigger in the northern hemisphere typically. And you can see that manifested in the 50 hectopascal zone mean temperature. So the southern summer, January, February, March, and then here's where, in this region, it's dark permanently over the South Pole, and there's a slight delay. It cools and cools and cools and cools. It's still cooling, so the cooling maximum, the lowest temperatures are always lagged relative to the cooling. Just like a rising parcel, when it's going the fastest, but you don't get to the coldest point until it stops. But in the northern hemisphere, here's the northern summer warm period. It's interrupted by polar heat fluxes and a reduction of the polar vortex much more strongly than you can only see just hints of it here in the southern hemisphere. And so then you can consider one apparently standard measure of the polar vortex is the area poleward of the minus 32 potential vorticity unit contour on the 450K surface. So that's around 20 kilometers, 21 kilometers altitude. And you can see the area growing, and then this year is a little bit bigger than the average. So that speaks to perhaps less wave driving this year than normal, rather than a variation in chlorofluorocarbons. Okay, how about a couple movies of what does the ozone hole really look like right now? First, comparing November averages across all of these years. So this is every average November ozone hole. And sometimes when it's yellow, that would be 2002 or 1986. But this very last one, it's pretty substantial. It's a competitor with previous big ozone holes. And it's circularly symmetric. We'll see, I made a movie, that's the last one that I'll show, which is 850K TV, where you just download daily maps and loop it. And that shows, yeah, it's slightly disturbed, but not very this year during October. So this one is 2020. I'll show it first because it allows us to appreciate how it goes away into December. And it does sometimes take all the way into the first week of January for the polar vortex to completely disappear. This is daily. It's a combination of a few different satellite instruments that can sense ozone. The ozone monitoring instrument, things like that. Okay, it starts in July. And this is the winter time, so you're going to start to form a polar vortex. And it's surrounded by a collar of relatively high ozone. The synoptic waves in the subtropics that propagate on the westerly jet, and a few mild planetary waves can take ozone from the sunlit tropics, and it tends to wrap anticyclonically and sink and appear on the backside of anticyclones in the subtropics, so you get a ring of high ozone. But it takes a long time to revert to. There's still a hint of cool here from the previous summer, and this is the end of December. So it takes a while to actually become a full-blown summer vortex, and that happens from the top down. And I think it's a mystery in both the northern and southern hemispheres as to what is the residual of the polar vortex at the base of the stratosphere? How long does it extend into the summertime in both hemispheres? And what does it mean? Is it important for understanding late spring, early summer weather? Okay, this one is for this year, and it stops just a couple of days ago, I think November 1st, but it shows, well, this year is pretty robust too. So again, this is column ozone in Dobson units. So this might be 400 Dobson units out here, and in here, I guess it doesn't show the color bar, but that's probably 150 Dobson units. Something like that. So you lose 50% of your ozone in just a few weeks over the South Pole.
I got a question. How different would that be without anthropogenic effects?
Yeah, I think people have made pretty good maps of this from before 1980, and it's, yeah, you have a real vortex. It's a natural vortex. So unfortunately in the press in the 80s, people went a little bit too far and said, you know, there's this huge thing that happened that we've never seen before ever. Well, no, that's not true. There is a natural ozone hole over the South Pole that was known by Deutsch. He had a diagram latitude time where he compiled all sorts of measurements of Unker measurements of watching the moon or the sun step through the atmosphere, and you can do conversion techniques to get an ozone profile. And he found that there was a collar of highish ozone around, say, 50 south, and that poleward of that, over the South Pole, there was less ozone, maybe 200. But, so, That's a natural ozone hole. And it's always good to interact with the public by saying that's the case. But with the advent of chlorofluorocarbons, it's just gotten so much deeper. Instead of 250 Dobson units, it's 100 Dobson units. So that's the difference. I mean, it's a natural thing because of the lack of waviness in the southern hemisphere to disturb the vortex. The vortex is just so strong. The lack of continentality allows that to happen, and so it's a radiatively determined vortex.
So Matt, you showed us this distribution of ozone near the South Pole, over the South Pole over Antarctica. The question would be, dynamically, can we see trends in circulation changes in the southern hemisphere due to the recovery of the ozone in that hole?
Yes, people speak about possible feedbacks. They impose a filling ozone hole in climate simulations for the next 100 years, like CMITRONs. And there are some interesting possible effects on tropospheric jet position based on that, but those all involve vertical coupling with annular modes, and that's still, I think, a partly developed idea. It's hard to know exactly. A related question people have asked, well, if you deplete some ozone and then you let the depleted ozone air mix out all over the hemisphere and into the northern hemisphere eventually, and into the troposphere, is that a net global loss? Is there like a ratchet? Every winter in the southern hemisphere there's local loss, but it mixes out, so the global amount gets ratcheted down by the process. I don't know. People say, yeah, southern hemisphere without northern hemisphere. I don't think I really answered your question. But I think it's a good topic, a complicated topic. I remember talking with John Kutzbach. He wanted to do paleoclimate simulations where we impose ozone changes related to like an asteroid impact or something. Those are hard to know. There's a recent study that came out about nuclear winter. If Russia and the US or China decided to have at it, what would be the effect? And one of their main concerns is that the smoke might fall out sooner than the nitrogen compounds created by the explosions that would destroy ozone. So at first, the smoke would protect you from, but then you'd have a few years where it's way too sunny in the ultraviolet, and you have to protect yourself. Or other organisms, but besides humans, are sensitive to too much ultraviolet too. So that would be a possible threat to crops.
I have a question real quick. The years that were not anomalously low, 98 or 2002 that you mentioned, in the same sort of loop there, is the wave driving that you're speaking of, the synoptic and planetary waves that we can see on the periphery? So in one of those years it lights up more than others, and then all of a sudden the ozone hole sort of gets folded over.
Yes, yeah. The 2002 one, I believe, happened with an unusually strong development of an upper-level anticyclone over South Africa, and so it put a forward dent in the base of the vortex, and that sort of boundary condition at the bottom, it just caused it to start to wobble, and you could see the upward progression of a wobbly pattern. It took 3 weeks before, I think that happened August 28th or so in 2002, and then by September 21st, finally it wobbled and the energy was going up from that disturbance, and the vortex started to form a dumbbell shape, and there was material that went over the hole in that one on September 21st. But that process of energy just going through that depth of maybe 350 Kelvin up to say 850 Kelvin, that might take a few weeks for that process to unfold. So the last one is just a very brief movie, but it does show some of these wavy features. I'm used to seeing either evidence of synoptic disturbances, there usually 5 or 6, and the tops wherever there's anticyclones, it depresses the tropos upward, so there's less room above, and so low column ozone is correlated with traveling synoptic anticyclones, and high column ozone for the lower tropoplasm in a trough. And so that kind of 5 or 6 wave number pattern is often seen in column ozone. This particular one seems to show a wave number 3 pattern mostly. So it takes a little while to download each one. So I only did 1 month last night, but I don't know if that's SpongeBob SquarePants in a swimming pool. It's 850K potential vorticity, which is in the upper stratosphere, mid-upper stratosphere, and so high negative values are over the pole is at this big, and so this is the edge of the polar vortex right here. A hint of a wave number 3, and we can just kind of go through it once quickly, and then I'll go back again. So sort of a wave number 3, but there are other things happening. Eastward rotation, a little bit slower than the mean flow, because Rossby waves travel westward compared to the mean flow, but the mean flow is fast. So the waves do go eastward. This method isn't terribly flexible. Oh, I guess I can go up and down with the keys if you see. Yeah, I can go down. All right. So this little anticyclone is sort of of interest, and it does happen more often near Indonesia. I don't know if it's related to thunderstorm complexes in Indonesia than outflow, and then the cyclonic wrap-up. And ozone will come down and around behind, and so you tend to get a column of high ozone here. But this is PV. You could maybe argue that this is kind of is consistent with a trough downstream of it. But there's a wave number 3 pattern. Here's another anticyclone. It's a tropical anticyclone. So that one's kind of big, but then it tends to elongate. Oh, here's more of a wave 2 pattern. So I guess you can go back and forth in thinking about, is it a good thing to think of this in terms of a zonal pattern plus a wave number 1 pattern plus a wave number 2 pattern plus a wave number 3 pattern? And then this transition right here, you'd have to have some interaction coefficients where, how do I get wave energy to go from wave number 3 to wave number 2? You can do all that, but it's a bit of bookkeeping. And so I think a more conceptually clean picture is if you're looking at the whole vortex as an entity, you can just watch its Lagrangian evolution, and it kind of makes some intuitive sense. Oh, there's another streamer coming out of the tropics, see? Like that. So when a trough dips into the tropics, then it grabs tropical PV air and it comes out and around. In the northern hemisphere, if that wraps up over the Pacific, that's called the Aleutian high. That's very common. But the southern hemisphere, those things don't ever really go right over the pole, except once in a while. So you can see a kind of a hint of Rossby wave breaking here. This trailing streamers, this vortex interacts with this vortex. They tend to shred each other on the edges, and you can see this little polar PV streamer there. Rossby wave breaking signature. So there's some mixing going on. And if you deplete ozone there, that depleted ozone air will come out into the tropics. I think the main thing there is that the tropics are so much under photochemical control for ozone that it's really hard for diminished ozone over the South Pole to have an effect on the other hemisphere. Okay, that's all I wanted to show. Thanks for listening.
Thanks, Matt.
I don't know if there are any more questions or
Yeah, any questions? Thanks again, Matt, for that presentation. It's really interesting to see a part of the world we don't normally look at a particular level that we don't traditionally see it come out here.
I just have a quick question. Talk about the waves refracting back down into the troposphere. Is that due to like the shear reversal? Typically talk a lot about the superposition of the polar jet, subtropical, and the polar night jet, the subtropical jet. And to me, that would allow westerly winds through the depth of the troposphere and well into the stratosphere. Is that sort of the wave guide? Westerly winds that allow?
Yeah, in zonal mean linear theory, those two would add together in the northern hemisphere, make a more continuous regime. In the southern hemisphere, the subtropical westerly jet is really straight, and it's only on one side, and it does seem to be decoupled from the polar night jet. But in the southern hemisphere, the polar night jet is often vertically continuous down all the way to the surface, and I guess you could call that the subpolar night jet. In the northern hemisphere, the polar night jet and the subpolar jet seem to be more distinct entities, roughly. But yeah, so there's the idea of the critical surface, which happens in easterlies. If you have stationary Rossby wave energy, you can't get into easterlies. And so there's a critical surface, the wave energy is absorbed. The turning surface is just really flaming westerlies. The phase surfaces can become vertical and then turn over, so the wave number, vertical wave number M goes through 0. The energy comes back out. That's one aspect of how you can have adaptive synoptic waves, I suppose.
Well, I see things a little differently there, in that the subtropical jets from the southern hemisphere interact strongly with the polar night jet. And they're doing it right
Okay.
now. And what you see happening is, when you look at it three-dimensionally from the side, you can see that where the subtropical jets come underneath the polar night jet, they form a bridge, and there's a continuous high velocity all the way up and down. So there's a reversal of thermal wind in the middle lower stratosphere. There's a reversal of thermal wind from the subtropical jets, and that allows the wind to build down to a lower elevation. So if you look at the polar night jet, just stretch it out as a vortex, it gets lower, it gets higher, it gets lower, it gets higher, where it's being intersected by subtropical jets.
Yeah, there's some spiral features that appear where the subtropical westerly jet over the western Pacific kind of tends to go forward and trace it all the way around.
Now,
There's
we
various
can look at this. I
configurations.
find it really fascinating. I know this happens, and it does correspond to weather at low elevations. That doesn't exist if you don't have the polar night jet.
I think your approach is very insightful, and maybe later today you can show more.
I think we need to reconcile, what we're seeing, what you're looking at with weather maps versus what you see actually happening three-dimensionally. And I think there's a lot of things that are not well understood at this.
Three-dimensionally, if you're talking about the critical surface being the easterly, if you can superimpose westerlies on top of each other, you no longer have a critical surface.
That's true. But in this system, if you have a pretty good westerly jet in the UTLS, and then there's vertically continuous westerlies to get strong, that could be a recipe for trapping synoptic wave energy. It's maybe, instead of allowing it to go, it depends on how strong. As a guess.
Greg, I asked Pete to go to your page. Is there something you wanted to?
Well, you can
go
see
point
this
out
is
from
today, and the polar night jet is at, the polar night jet is this one down here. It's not in polar stereographic or polar projection, but it's almost, it's almost circular. It's zonal on this map. And these are the subtropical jets, and you see, looking through this 40 meter per second three-dimensional surface, you see these subtropical jets actually entering inside the polar night jet, which means you're looking through the jet, and there's a continuous high velocity all the way down to where the subtropical jet intersects it. And this occurs often corresponding to what you were showing.
Now, I was only talking about monthly means.
Well,
so.
no, you were showing some animations of
Yeah.
wave number 3, wave number 2, and you see that same thing right here. In this particular case here, we're looking more like a wave number 2, maybe a wave number 3. It was wave number 5.
Material around the top of an anticyclone will come toward the pole.
What?
Material, so the forward deformation is an anticyclone, and it seems like it's coming around the equatorward side down into your subtropical jet will curl around the east side of the anticyclone.
The subtropical jets represent a push of cold air from the tropics in the lower stratosphere. And so these cold plumes come in and they reverse the thermal wind, so it's cold to the north here. And then instead of cold to the south for the ozone holders. And when you reverse the thermal wind, then the whole velocity profile extends down further. And that's what you see happening here. So I think it's important because when you get these intersections and the velocity profile extends down further, the quasi-geostrophic circulations associated with these jets are more likely to reach to the ground. especially when you get a subtropical jet that high of a latitude. And when you get the circulations of the ground, they tend to pick up that cold air and create lower tropospheric phenomena. So I think the interaction is important, but, and I don't know what the ozone hole means, but except what you were, this is consistent with what you were saying, is that this is pretty strong, this polar night jet at this time of year. Normally it's kind of withering. This is all we have at Arlington Pacific.
Huh.
It's starting.
Well, I guess I'm glad that you're not living in Nebraska, because they got frost and bad weather a long time ago. This year.
But, you know, I think it's interesting, even in that last picture, you can see a plume. As soon as we have the polar night jet, there was already a subtropical or tropical plume associated with the subtropical jet going up and punching into that little piece of a polar night jet.
It's almost like everything has to go through that pinch point in the tropics, and then the jets become unstable and are unpredictable to the east.
I don't know. I have to think about
When the
that.
outflow from Indonesia.
Yeah, I mean, what's coming from Indonesia is really a critical part of this.
This looks like.
Yeah, absolutely.
Well, thanks for that discussion and the question, Ian. So we're going to talk briefly about the weather of the United States. We'll focus on the development of an extratropical cyclone in the Gulf of Mexico, see some aspects of that. For those of you in 452 and 751, we've talked about sort of PD redistribution. We'll see some nice examples of that for the forecast. And we'll also look at this boundary that we'll see here is going to mark, I think, the leading edge of some warmer air that's going to arrive here in Wisconsin, with our temperatures perhaps getting into the middle, maybe even upper 60s over the weekend. So we have a brief warm-up that you can enjoy, particularly on Sunday. So here's the infrared satellite image. You can see a lot of low clouds that are kind of just trapped up against the Rocky Mountains in Mexico, the southern extent of those, but over Texas as well. You can see there's low clouds that are also, I'm not going to say it's fog yet, we'll look at the surface observations through the southeastern United States. And then in this enhanced infrared image, you're seeing really cold cloud tops, not necessarily producing significant precipitation. It could be a lot of high cirrus. We'll look at the radar in a moment and identify what's going on beneath them. But the developing cyclone is here to the eastern Gulf of Mexico. It's not really evident in terms of, if you look at the satellite imagery of a really clear, distinct cyclonic turning to the low level cloud. Maybe there's a hint of it here, but it's, again, this is an extratropical cyclone. On the west coast, we'll have high clouds filling in. We'll see if there's any precipitation associated with that. But really, it's with the exception of the Gulf of Mexico, and maybe just off the west coast of the United States, a pretty quiet weather day across the U.S. Let's go to the next tab, please, Pete, which is the radar. Here's the composite radar. You can see a little bit of light precipitation, over northern California. So there's that weather system that's approaching. Light precip in the Dakotas, particularly in North Dakota. We'll check to see the precip type on that, probably rain. And then a pretty extensive rain shield across the southeastern United States. Interesting sort of banded structure with this. And again, this is in association with the interaction of an upper trough with a lower tropospheric paraphytic zone, the early stages of cyclogenesis developing there. Next map is, we will look at the surface map. Large format, and we'll first just go over to Wisconsin. 48/28 with a southerly wind at 15 knots, and pretty decent weather here. Surprised that it's not really overcast, but it's really high clouds that are covering up our part of the state. And again, really quiet weather. As you go to the western, go far west, over parts of the eastern Dakotas, you can see some evidence of a wind shift in this region. And that's associated with that boundary that we saw on the satellite image. You can see that sort of band of cloudiness. And you'll note also that we're getting lots of warming to the west of that boundary. So this is a warm front that's begun to set up, relatively dry across the entire upper Midwest and the northern plains. But that boundary we see slowly advance eastward over the next couple of days. And again, this warm air is from some downsloping air off the Rocky Mountains into the high plains toward west. So we'll see that approaching us later on. If we go over to the northeastern United States, go to Worcester, Massachusetts. Professor Maroon and I are battling for first place here at Wisconsin. We're actually tied In the contest, it all comes down to the high temperature today. And Worcester, hopefully they stay on the cooler side of 50 as opposed to going higher than that, or higher than 49. But nice day over the northeast United States, and with some light northerly winds. The winds precip all the, and the minimum temperatures are all settled. It's all about the high temperature in Worcester that will determine who's on top here in Wisconsin at the end of this city. Let's go down to the southeast United States. And here we can see some increasing winds as we go closer to the Gulf Coast. I don't know if it's possible for you, I know we get the data, the buoy data out here over the Gulf as well, just to get a better sense of what's going on. But there's some evidence of the cyclonic circulation. The pressure's a little bit lower here, clearly, but there's no, we don't have the odds over the Gulf at this point. Really high dew points in the 70s in the southern part of Florida. We saw that yesterday. You can also see the baroclinicity at the surface. Part of that's due to the fact that they have cloud cover, so the northern part of the state, well, the entire state is cloudy, but as you go further to the north, you see the temperatures in the low 50s, all the way down to the mid-70s, and then in the Keys, the low 80s. So significant baroclinicity, and all the ingredients, the setup for what's necessary to trigger the development of the cyclones, like Pedersen's conception of how these cyclones develop an upper trough approach to pre-existing lower tropospheric baroclinic zone. All the ingredients in place as we look at some of the analyses shortly. Okay, let's go to the West Coast briefly. In California, we saw some of that precipitation. Yeah, Northern California, we see some light rain, but nothing pretty significant. So again, pretty quiet day across the continental United States. Okay, so let's now go to look at the upper tropospheric mass, the superpeaks. And we're going to start at 850 hectopascal. We're going to 850 first, please. So in that, you can see in the eastern Gulf of Mexico this morning, the weak 850 millibar minimum and geopotential. You can see the clear cyclonic circulation around this broad area of low pressure, or low heights, excuse me. And we can see the baroclinicity in the lower troposphere. It's not a well-defined front, but there is certainly a nice north-south temperature contrast, and that provides the energy, the available potential energy for a developing cyclone. Didn't talk about it much, but there's another weak cyclone developing along the baroclinic zone to the east, off the east coast of the United States. Over us, as you go to the west, you can see, the temperature gradients just from our longitude eastward, are relatively weak, but we have significant baroclinicity, horizontal temperature contrast from the Dakotas through the western part of our state. And with those winds out of the west, with this trough that's crossing the northern, just moving away from the Rocky Mountains, that's creating a nice plume of really warm air that's going to spread over the upper Midwest over the weekend. You can see hydrostatically the reflection of that warmth. You can see the thermal ridge and the trough almost coincident with the hydrostatic response to that warmth.
There's a hurricane or tropical cyclone.
Yeah, this is Loma out in the North Atlantic. I think it's a tropical storm, and it's
Has there ever been a Virgo-cane, like iceberg and a hurricane at the same time?
what's it?
A Virgo-cane. I don't know. Icebergs and a hurricane
Oh,
at the same time.
I don't know, but it might be a nice name for a drink. Yeah, this is actually Wanda, not Loma. Wanda out in the North Atlantic. But Wanda actually formed from an extratropical transition from an East Coast storm that occurred last week. I think you guys may have talked about that last week. Okay, let's go up a little bit to 500 hectopascal. Our surface cyclone east of the west of the Florida Peninsula. Here's our upper trough. You can see that. You can see the minimum in temperature here, minimum geopotential height. It's a pretty broad upper trough. It's not one that has significant curvature to it. But you can clearly see the cyclonic circulation, vorticity associated with it. And when we go to the upper Midwest, we'll see this in the forecast. Another trough at 500 millibars, which we'll see is associated with a thin PV structure that's extends from Alberta down into northern Wyoming. There's a nice broad difluent flow just to our west, but not much of a temperature gradient for it to act on at this point. Let's go up a little bit more to 300 hectopascal. And we can see down here, again, with that developing cyclone just off the east coast of the United States, we can see a nice jet entrance region that that's formed, and we have a little jetlet that's just off the North Carolina coast this morning, south of Wallops Island, eastward. And the trough that's the continuation of the trough is off 500 millibars and 200 millibars of the western Gulf. So it's this trough in the middle and upper troposphere interacting with the lower baroclinic zone, which is responsible for the beginning of the formation of this lower tropospheric cyclone. To our west, we see a nice strong westerly jet approaching the west coast of the United States. It's already made landfall, if you will, over the northwestern part of the United States. And that westerly flow over the Rocky Mountains are also going to provide further downsloping flow and help spread warmth eastward, as we'll see in the forecast going forward. So some warm times are ahead for us in the forecast. So let's next go to the UW-AOS, the MM5 tab. Time series. To start with the meteorograms, again, these temperatures in this model don't really do justice to what we're going to actually see. I think we'll probably add 10 degrees Celsius to each of these, particularly Sunday's high temperature will probably be in the middle to upper 60s on some days. But it gives you the broad sense that temperatures are going to be increasing over the course of the weekend, as well as the dew points being declined, but they're not going to become unbearable. And this is suggesting maybe a very slight chance or some light precipitation here, but I don't think that's really going to be in the cards. Let's next go to the time height section, please, Pete. Now, the time height section, what we see are a couple of interesting things. Again, the yellow contours are the isotropes. You'll notice a general slope of these isotropes in time downward that indicates warming in the lower troposphere. You also see clearly during these periods of warming, significant, some modest and significant varying of the winds with height. Assuming the winds are nearly geostrophic, some of this is going to be due to, that's an indication of temperature, of warm temperature reduction, so increasing temperatures aloft. The model's forecasting, sort of modestly breezy conditions this afternoon as a low mixed layer begins to thin, low mixed layer begins to form this afternoon. Cool off overnight, relative humidities go up. And then we mix tomorrow. It's not going to be well mixed, but we're going to be a bit warmer tomorrow by several degrees Celsius. Today getting up to 282, tomorrow probably 282 to 285. And then, I don't think the representation of the warming is really evident here, but we could probably be again into the 5 degrees Celsius warmer on Sunday. In the upper troposphere, interestingly enough, we have this trough that goes by. You can see the southwest winds ahead of it and the northwest winds behind it. You can see the isotropes bowing up beneath this upper PV structure, localized maximum of PV. And so that's going to be consistent with ascent as the trough approaches, descent as it moves away. But none of that. It's a really small feature, which means its horizontal length scale means its penetration depth isn't going to be particularly large. And so you don't see much influence down here at 750, 800 millibars. So all of the stretching that's occurring with this and the change in temperature structure beneath this upper trough is really confined to the middle and upper troposphere. It doesn't really sink down. And we're not going to feel the effects of that down here as it passes by.
Unless there's cloudiness.
Unless there's so if there were clouds with it, and the relative humidity is, again, 70% here, upper troposphere, there's very little going on with that. Right, you're absolutely correct. If there are clouds associated with it, then we're going to see that can impact the radiation at the surface, but in terms of dynamical features, not thermodynamic features, or microphysical properties, not much is going to happen down here. Okay, so let's actually see what does it look like on a map. First thing I want to do is just do a loop. Let's start here. Let's actually not do the loop. Let's go to 6 hours in the forecast. First of all, to show you this cyclone in the southeastern United States. Significant precipitation associated with it. It's supposed to be at 1,011 by this time today. Broad anticyclonic circulation over the central and eastern United States. And here's the beginning of warm advection just to our west. The precipitation that we saw in the southeast, again, that shows up really well as the baroclinicity, as you see in the 500 to 1,000 millibar thickness field. And there's a developing cyclone off the east coast. One note I'll make is in our weather discussion on Thursday, yesterday, we were talking about how that trough that we saw propagating over Michigan was probably not going to excite much of a significant cyclone. I think we're actually getting something a little bit more exciting than was predicted by the models off the east coast today. And so that's something I would note in passing. The trough that we saw and the surface cyclone associated with it over Saskatchewan and Manitoba with the trailing cold front, but here's the warm front that's advancing eastward. That's going to be introduced the stronger warm advection later on over the weekend. So let's go ahead 12 hours to 18 hours of forecast of this evening. There's our cyclone. At least in this model, it doesn't deepen much, but you can see significant precipitation, close to 4 inches in the 6-hour period ending at this map time as the cyclone develops. The pressure gradient is significant, largely because of the strong high to the north and slightly lower pressures to the south. Remember, if you're calculating the geostrophic wind down here for this gradient versus up here, this will be stronger, associated with stronger winds because of the F in the denominator, Coriolis parameter in the denominator. Even though they're comparable, or nearly comparable horizontal pressure gradients, it's going to have a much bigger impact on the winds down here because of the lower latitude. Okay. But for us, pretty quiet, increasing southwesterly winds overnight tonight. Let's go to the map 12 hours later. So mid-afternoon tomorrow. This is now begun to really deepen down to 1,007 hectopascal. Stronger pressure gradient, and again, significant precip. And I keep emphasizing the precipitation. You can also see the S-shape forming in the ice and the thickness contours as we're getting a fairly well-defined warm front and cold front associated with this weather system. The precipitation is going to indicate, if you look at potential vorticity diagnostics during this time period, should be indicative of a redistribution of PV. Increasing PV beneath the region of maximum heating and decreases aloft, and we'll see if we can see evidence for that. Model suggesting some very light precip, but I think that's just how the microphysics will be handled because I don't think there should be much in the way of precipitation as this weather system passes by. We have the warm front will pass by tomorrow. Then we're going to be in this region of maybe temporarily weak cold advection with another surge of warmth is coming for Sunday. Let's go to the next map, 12 hours further. Then we'll do a loop. So 42 hours for a night. Down to 1,005 now, and with significant precipitation and deep, maybe even convective precipitation occurring out over the Gulf Stream. We're getting these isolated minima in sea level pressure, but this is, again, a broad cyclonic circulation, probably and very likely beach erosion across the South Carolina, North Carolina, and Georgia coast, maybe even down to Jacksonville with strong winds as the cyclone slowly deepens. It doesn't really move rapidly away. You can hear that slight chance of precipitation. But here's the strong warm advection about to start up again. And let's go to 60 hours to finish this series of maps off, then we'll look at a few diagnostics. So the cyclone, just a broad area of low pressure, begins to fill a little bit, less intense, and again, strong winds are now beginning to subside along the coastal sections of the southeastern United States, and that warm advection is sort of in place over us for Sunday evening. Let's look first at the lower tropospheric PV, so the 305 to 315 potential vorticity, and let's first just loop it and we'll hopefully be able to see that. So we're looking at potential vorticity in an isentropic layer. To the extent that the flow is purely adiabatic, we'd expect any change in potential vorticity we see at a given location would have to be explainable by horizontal advection. If you see things being created in this, or the PV getting larger at this layer, at this level, as we animate it, that's an indication that there's diabatic heating occurring above this isentropic layer, and so we're getting PV redistribution with higher PV being created beneath the region of heating. And indeed, we do see, as we evolve this map, we go from these light blues to dark blues to greens, and that's an increase in potential vorticity. We can't explain it by simply just convecting it, the wind's transporting it. There's actually a generation of PV in the lower troposphere. And that's going to help with the spin up of the surface light. If we go to an isentropic layer a little bit further up, let's try that. We can go to 315 to 325. We also see some generation of PV there, but we also see areas in which the potential vorticity is beginning to decrease, just to the west and northwest of the where we see the generation occurring. And let's go up one more layer. Seems to be more evident there. But we see a really interesting anomaly, which we'll talk about on Tuesday in 452, 751. Notice this upper trough, maybe we'll just stop it and just step forward. We can just go back.
Sure. Well, just the images, right?
I'm sorry?
I get stuff again.
Yeah, that one was, we don't have an FLI on that, but let's go to, before that time, let's go to the first time on this first, please. 0 hour, yeah. So here's that upper trough. We can see evidence of it 6 hours in the forecast out over the Gulf of Mexico. And then let's go ahead. Notice that there's a bit of a ridge downstream of it, so that's kind of nice, at least in this field. Let's go ahead 12 hours. That layer. Still see it, but we see this notch that's still here. So this is PV trying to be vectored northward. This notch sort of remains. I think part of this might be due to some diabatic heating occurring. But the trough, the structure is changing a little bit. Notice if you were to get heating here or deplete the potential vorticity in this region with this advancing upper trough, you're changing the curvature, the wavelength of this feature, getting smaller, and that means the advections are going to go up significantly. So this is making a more favorable pattern for this upper trough to interact with anything at the surface. We're increasing the vorticity advection over this layer. Let's go ahead another 6 hours. So that should work. Again, you still have the structure right here, but you can see increasing curvature from cyclonically turning flow. Let's look at the periphery of this PV contour, the isoplectic PV here. You can see it's getting sharper. Notice the sharper gradient here as well. Even though these winds look like they're nearly parallel to the PD contours, there's perhaps a small gradient, or there's something that's creating confluence along the edge of this. And my interpretation of this would be there's some of the diabatic heating that's occurring out over here is helping to influence the diverging outflow to tighten up those gradients. Compare the PD gradients here with the gradients here, which really tight on the edge of that upper trough. Let's go ahead another 12 hours. All right, air eventually is going to get heading further to the north. You can see these purples that are occurring, which we didn't see before. We saw some of these light blue contours here. And so some of this wrap up and some of this, the strengthening of the gradient, I think, was due to a PV redistribution, creation in the low levels, decrease at a loft that's associated with heating between those two layers.
Well, it looks like a Tropospheric fold right there, too.
You mean this structure here, or just the fold?
No, up on.
Right here?
Yeah.
Yeah, so it's hard to see it from this perspective. We'd want to look at a, do a cross section through this, or look at a tropopause map to see how which PV structure is it going underneath or above.
Well, it would be obvious that the high PV is coming from above, and the low PV would be coming up from below. It's in terms of a fold, right?
But yeah, or the stratospheric PV is coming equatorward along an isentrope that's at a lower level than the upper tropospheric PV that's rising over it.
So it's like something like this.
Yeah.
Yeah.
Yeah, that's what you were saying.
That's what I'm saying, yeah.
This is really interesting. It reminds me of when you first showed the loop that it merged back in. Maybe I'll wait till you.
Yeah, let's actually just let's go to the loop. Let's go back to the loop.
Because people who do Lagrangian particle trajectories for stratospheric exchange and they try to quantify, there's always this troublesome the merging events back into the stratosphere.
Mm-hmm.
Nope, you're not really in the troposphere yet. And so they have to count them. There's sometimes 3 or 4 events for a given particle. Once it's sequestered in the tropospheric air, it may return to the stratosphere.
That's right, and part of this is going to be the reattachment of these PV contours has to be in a non-conservative process, right? You can't just do it.
Some turbulence.
Turbulence, perhaps, that's doing it. The other thing, if I'd gone longer with this, you can see this rapid decrease in potential vorticity off the North Carolina coast at this level, and that's again associated with some of these convective or really intense precipitation structures that were occurring just off the East Coast.
But that low PV tropospheric intrusion really seems to be dissolving into the stratosphere.
This right
the
here?
one over the Great Lakes there, the blue patch.
Yeah. So here,
Yeah, and then
this
it
feature.
just
Right.
mixes in.
Yeah, this is a pretty coarse resolution model run, and so the physics of what's going on with that, we probably will look at some other ones. But if you look at plumes, look, here's another plume of very low potential vorticity air coming across the west coast of the United States, south of that jet. And notice how it begins to arc up into our latitude. And this is sort of their recreation of a pattern we saw several weeks ago when we were relatively mild with these rejections of subtropical PV over the central part of the United States. And from things that Greg has talked a lot about, and I think that's typically associated with our having at least brief warm-ups and much milder weather, as the tropical jet itself is now north of our latitude. I don't know if you would concur with that, Greg?
Yeah, absolutely.
Okay, so let's get out of this. Please look at 850 millibars, look at the temperatures at 850. Oh, you can do a loop. This will be quick. Oh, not over us, right? I mean, over the whole U.S. All right. So you'll see those isotherms kind of wrapping up with a cyclone that develops there. So again, here comes this surge of warmth. Briefly, we get it tomorrow, but then cold advection comes in tomorrow evening briefly. And then you'll see this warmth as we get air flowing across the Rocky Mountains, but also at upper levels, the tropical jet lives north of our latitude, and that just creates significant warmth over it. So the forecasted high in the models, the ADA and the NAM, are in the around 60 degrees. Weather Service is going 64, and I think, yeah, this is going to be a situation where if we can mix out, we can get much warmer than that. The days are shorter, acknowledge that. The ground is moist, but I think we have a chance. I think the models, the statistical interpolation from the models is probably underdoing this. So I would say probably 65 to 68 is probably a good 20 feet for us on Sunday for a nice warm-up. Let's get out of this and go to the pivotal. I think I have one pivotal map up. Let me look ahead. We are getting the warm-up, but maybe I don't have it up there, so we'll just go to pivotal. There it is. And we'll get the warm-up. And here's the cyclone here in the southeastern United States. I'm not going to focus on that too much, but let's just go to 60 hours Sunday evening at the end of the MM5 forecast period. There's that cyclone. It's a bit more intense than the GFS.
I should point out, just as a point of interest, that first map you had up there with the cyclone in the Gulf, that's the classic situation for snow in Tallahassee. It happens once every 15 years or so, and it has to be much colder in January.
Right. You have this broad Arctic high that would be over the eastern United States. Yeah, and the low tracking much further to the south of Tallahassee. You get the cold advection. If this were winter, midwinter, potentially snow. And it'd be one of these things where people on the East Coast will be wondering, is it going to creep far enough north for them to get snow? So let's go to 60 hours. We saw that the cyclone's out over the Atlantic. The warm-up has occurred over us. Broad, southerly, really strong winds, geostrophic winds. But let's watch what happens. Because I think this time next week we'll be shivering with maybe snow in the air. If the forecast verifies. You can go anyway. 108 is good. Jump ahead 2 days. The cyclone's still out here, but we have an anticyclone that's sort of parked up over us. So cooling off by midweek on Wednesday, and let's go ahead to 156. And we're going to undergo a rapid transition to something that looks more interesting. Because of time, we can't look at the overall evolution of this. But the forecast model today, and we can look back at other runs, is forecasting a pretty decent mid-latitude cyclone over the northern part of the state. It seems like this time of year, late October to early November, we often get one of these big cyclones that's really windy. This may be one of them, with a nice, well-defined cold front, which will be nice since we'll begin talking about that in 452. Nice cyclone center that's developed. And we go ahead to 168 hours, so Friday morning of next week, that cold air comes roaring in here. At least this simulation, or this forecast has us maybe get some light snow and really windy conditions. If you look at the temperatures on Friday morning, let's go to 174 hours, 6 hours further in, so weather watch time, and go down to, this will be noon then. Temperature-wise, middle of the day, temperatures over Madison just around freezing or up, slightly above freezing. So it'll feel like winter. And if you look at the wind chills, chilly with wind chills in the low 20s. Just out of curiosity, if you go back to the surface map, please, and scroll down just a bit, and then we'll go to, let's look at the 0-0 run to see if we have something similar. Don't want to buy a forecast until we've seen at least a few. Look at that, totally different. Cold, maybe there was some snow, but it's not a really intense cyclone. 6-hour forecast, or the 6E forecast from the same value at the same time. Somewhere in between the two. So looks like the predictability of what's going to happen a week from now is still relatively low. The most recent run suggests a significant cool down for us. We'll see how that all works out. Anyway, thank you, Matt. Thank you, Greg. Thank you, Pete, for leading, helping to drive things, Matt, for the discussion, and Greg and Matt for that discussion about the interaction with the tropical jet and the flow of low latitude, high latitude. And thank you all for being here in the
We should talk a lot about this.
Oh, yeah, we can do that.
What I see here. They're actually- A lot of this.
Oh, okay, yeah. Go to the-